Welcome to our webinar, and we're very happy to have you here today. And want to introduce a little bit about Engineering Practice Magazine, a little bit about IACPE, introduce our speaker, and talk about compressor studies. So we're very happy you're here today. So in 1997, we started KLM Technology Group, and we've been providing engineering operations and maintenance support for the hydrocarbon processing industry. 2007, we started developing engineering design guidelines. And there's about 100 plus engineering design guidelines we've developed in the last 14 years. In 2014, we renamed the engineering design guidelines to the Coleman's Handbook of Process Equipment Design. And so KLM's core business is we do training, we do the handbook, process optimization studies, we do hazard facilitation, engineering support, and specialized equipment. If you've searched anything on the web, you've probably seen these documents. And so there's one on pumps, compressors, control valves, relief valves. There's one on compressors, which we're discussing today. So there's about 100 plus of these. And so what I would do, I'd get emails from students asking for discounts. The handbook is mostly purchased by companies, so the cost is high. So in June of 14, we developed an idea to start an engineering association, utilize the handbook to train and certify individuals at a student rate. We're now in our 7th year of the association. And then in April, the following April, we started Engineering Practice Magazine. And so now we're in the 6th year publishing the magazine. And so basically, companies buy the handbook. And so they get very expensive. All right. So the company, and so we chose to offer IACPE, which is very low cost. And so we think that if you're looking for a good practical thing to do to help your career, to go get IACPE certification. So the first issue of Engineering Practice Magazine was April 15th. We're now in our 6th year. We're approaching 2,000 readership per issue. I am in amazement how much, how good the readership is. And part of our readership is our authors, like our speaker today, that writes for us every 2 months. And so with our readership, you should consider publishing and advertising an Engineering Practice Magazine. Current Alexa ratings, Alexa.com is an Amazon company that ranks overall readership. Google and the other search engines tend to rank just search engines, just search. This is overall readership, and we're very pleased. Engineering Practice is third best engineering magazine in the world, and so I'm still kind of amazed, but I'm happy and pleased. So what are we going to do today? We're going to talk a brief guide to gas compressor operability studies. We have a great speaker, and plant operability studies have been a part of the parcel of engineering design the last 25 years. Such studies are dictated by necessary at the design stage to root out operational issues, meet production specifications, operational requirements, and avoid plant downtime. And who is this guy? Well, nice looking guy there. Holds a master's degree in chemical engineering. Is a chartered engineer from Institute of Chemical Engineers, also an industry advisory member with IACPE. His expertise over 14 years of experience covers front-end engineering, process dynamic simulation, subsea, pipeline flow assurance, the oil and gas industry. He's worked for upstream process engineer with major conglomerates, and so we're very happy to have him today with us. So let me share his slides, and we'll kick off this. So can you see his slides? Can you see your slides? Okay, all right. So welcome our speaker. And whenever you're ready to move to the next slide, just say next.
Yeah, thank you all for having invited me. Special thanks to Mr. Hulmetz. So I think we have about 1 hour today. So I'll keep this presentation short and sweet without dragging it too long. I'll take about, let's say, 40 to 45 minutes to speak. And then in case you have any questions to ask, please do ask. We'll take the last 15 minutes towards that.
There's
Oh,
a
where is it?
there's a question and answer poll. You can so there's any questions you have at any time, you can type them in the question and answer panel. I'm sorry, I should have said that already. Go ahead.
No, you can if you wish to. Anyway, so I'll so we go to the next slide. Hello.
Yes. Okay.
Yeah. So okay, so the way I've put the presentation is that, you know, because the idea is, what is it that you should know? What is it that an engineer should know before even getting into any kind of dynamic simulation, for specifically for gas compressors. So I will be covering only on centrifugal compressors and not on reciprocating machines here. So the first thing is that you should have a basic idea of what are called performance curves. We can also call them system characteristics. Then what kind of drivers are required, and some of the basic operations, a startup, a normal shutdown, and an ESD. And then I put a point here saying system design philosophy, but it's going to be really hard to finish it off in this session. But I'll skip that, and I'll talk about what are the basic requirements of an anti-surge system, what are the characteristics of an anti-surge valve, what kind of recycle arrangements can be followed when you work on any gas compressor system. So we go to the next slide, sir. Yeah. So the first thing is to characterize a gas compressor, you need three variables: the polytropic head, the volumetric flow rate, and the polytropic efficiency. Now, in reality, gas compression can be achieved by isothermal methods, but this is too theoretical. In reality, you can never achieve isothermal. So that means when you compress a blob of gas, its temperature will rise. If you do not want the temperature to rise, you have to find a way to remove the heat constantly. Or what we say, you compress it in such a way that, you know, in infinitesimally small number of steps, if you try to do it, the temperature doesn't change. So you cannot achieve isothermal compressibility. The second type is called adiabatic compression, which means that there is no heat escaping from the system. That is, there's no heat escaping from the compressor casing. But again, this is too ideal. It is not possible. So in reality, what we have is when a blob of gas is compressed, the temperature will rise and some of the heat will escape. So for that reason, we simply say polytropic. But you're taking into account the heat transfer. So hence we say polytropic. This is a very simple way of explaining it. Now, when you have to do a dynamic simulation, you need two basic data. One is polytropic head versus volumetric flow rate, and polytropic efficiency versus the actual volumetric flow rate. Now, can I have control of the slides, sir? Because I can use the mouse to explain.
You would have to put up your.
I'll have to. Yeah.
Yeah. Okay. You'll have to put up.
Yeah.
Yes. Okay. You'll have to. Okay. Go ahead. All right. Yeah. Okay.
So when we look at the plot of polytropic head versus volumetric flow rate, you'll have a parabolic curve. So for various speeds. So in theory, you can, if you can run a compressor at, you can run a compressor at any speed you want. But then there are certain limitations, mechanical limitations, structural limitations. So for a given speed, you have a certain amount of head being produced against a certain amount of volumetric flow rate. So performance curves are a plot between polytropic head versus volumetric flow rate for various speeds. Now on the left-hand side, you have what is called a surge line. On the right-hand side is the stone wall region, which we also call it as choke flow region. Now, as the name suggests, if you push too much gas into a gas compressor, it will choke. Pretty similar to if you push too much food into your mouth, you will choke. The same way, a gas compressor will also choke. Now, we wouldn't want to run a gas compressor in the stone wall region. But if we go to the left-hand side where it says surge line, we don't want that also. So surge is defined as a flow reversal inside a gas compressor. Now, when that happens, it causes mechanical damage. Now, what manufacturers do is that they will give you these maps, head versus flow rate. Now, when they give it to you, you are supposed to operate the gas compressor only within this envelope. But then as you keep approaching the surge line, if the operating point is moving towards the surge line, there's a good chance that the operating point can jump across, and we don't want that to happen. So what we do is we operate the gas compressor with a certain amount of margin, and that's called a surge margin. We can have anywhere between 7% to even 15 or sometimes even 20%. Now the thing is that the closer you move to the surge line, the gas compressor the amount of power absorbed would be lower. But if you move towards the Stonewall region, the amount of power absorbed would be higher. So the idea is to operate the gas compressor within this operating envelope, and also such that the operating point represents the maximum efficiency point in one of these curves. Now, I put an expression here below, which says HP is the polytropic head. It's a function of the compressibility factor, the pressure ratio, and the molecular weight of the gas. Now, this is very similar to a pump, because pumps are for liquids, gas compressors are for vapors. In a pump, we simply say head, the power is head multiplied by the flow rate, by the mass flow rate. It's the same thing here, except that because gas is compressible, what we do is we take into account the pressure ratio, the compressibility factor, and the molecular weight of the gas. It's not really very different from a pump. It's just the compressibility effects are being accounted for. So the key takeaway from this slide is every gas compressor is characterized by its polytropic head, the volumetric flow rate, and its polytropic efficiency. You can run a compressor at any speed subjected to certain limitations. For a given speed, there's a certain head produced for a given volumetric flow rate. On the left-hand side of the performance curve is called a surge line. When the vendor gives you these curves, it's understood. Your guarantees and warranties are provided as long as you stay away from the surge line. So if you run the gas compressor in the Stonewall region, you're choking it. When you're choking it, in the long run, what happens is that you can have metal loss, because there's simply too much gas inside the gas compressor. And it is also, the efficiency also drops drastically. It's not a very efficient process that way. And then the surge margin can be taken anywhere between, I've written 10 to 12% here. It can also mean 7% to even around, let's say, 20%. Operating it closer to the surge line means the gas compressor will require less power to compress the same amount of gas for a given pressure ratio. But we wouldn't want that to happen, because it's quite easy for the operating point to jump across into the surge line, and we don't want that to happen. So the key takeaway is the compressor has to be operated within the surge limits. Next slide, sir. Yeah. Okay. So the next slide is about what kind of drivers can I use to operate a gas compressor. Now, traditionally, years ago, what we can call the Victorian era, steam turbines were used, and it's the oldest mechanism. The only trouble is that it has high capital costs, because if you want a steam turbine, you need steam. And if you want steam, you have to have a boiler, all the associated piping, the safety measures. So, and maintenance is another headache. So you can have scale formation. The water sometimes has to be polished if you don't get the right specifications. But there's an advantage. With steam turbines, you can hit as high as 600 or 700 megawatts easily. At least in present times. But steam turbines are not really used as much as they were, let's say, before World War II, let's say. In the Victorian times, steam turbines were also used, but we don't use it so much nowadays. Maybe in the power plant industry, yes, because you have to produce, because 600 or 700 megawatts is, let's say you have a 1 gigawatt plant. That's too small, but just for the sake of, for power generations, you can continue to use steam turbines. But to drive a gas compressor, not so much. But in the fertilizer industry, people sometimes still use them, a steam turbine. At least that's what I saw once a long time ago. Then, post World War II, with the invention of the gas turbine, what happened was because a gas turbine was invented to fly a plane. That was the basic intention. But with time, what happened was, if you remember, a gas turbine has an aeroplane engine has a big fan in front of it. Let's say you pulled it out and coupled it with a gas compressor, you can still run it. So somewhere around the 50s or 60s, what happened was people started using gas turbines. So, and in the last 30 years, not even 30, let's say 40 years, it's been used quite a lot. The disadvantages is, of course, COX and NOx. But you see, the thing is that the way you choose your driver depends on where you are. So let's say you're in the middle of the desert, no water, so you can't use a steam turbine. Let's say you don't have a substation nearby, you can't even use an electric motor. So what do? You take a portion of the gas coming out of the well and you route it to the gas turbine. And that's how the gas turbine runs, and then which in turn drives the gas compressor. So depending on the location, so let's say you're in a location where there isn't enough water, no power, then you go for a gas turbine. The trouble with gas turbines is you will have emissions, COX and NOx, and gas turbine efficiency is at least, I think now it could be, depending on the capacities, it can be anywhere between 26, 27% to even as high as I think 50, 52. That's 50, 52, yes, but mostly you can take it in the range of 35 to 45%. They're not really as efficient as electric motors. And of course, intensive maintenance, because you have a burner inside the gas turbine. When you have such high temperatures like 600, 700 degrees Celsius, so what happens is that you can have thermal cracking issues. You can have a layer of carbon soot forming inside. You simply have to keep, you have to put efforts to do maintenance on them. Now, because gas turbines were originally invented to fly a plane, and then it was used to, then it was modified to drive gas turbines, we call them aeroderivative turbines. Now, aeroderivative turbines are used mostly in offshore facilities because they are smaller and they are lightweight. But then for onshore applications, you can use what is called an LM. I think if I remember the name, LM stands for land and marine applications. So the same gas turbine can be used onshore also, but it's just that it goes with a different name. Aeroderivative turbines are more applicable for offshore applications. Now, the thing is that a gas compressor can rotate at any speed. So sometimes when the amount of gas flowing inside is lower, if you have to reduce the speed, a gas turbine is useful. So you can have a single shaft gas turbine or a twin shaft gas turbine. Single shaft is for power generation, because let's say if you want 50 hertz power or 60 hertz power, the gas turbine must rotate only at that particular speed. There's no question of varying the speed. Whereas for gas compressor applications, to alter the speed, you can have twin shaft design. So you have one shaft rotating at one particular speed and the other shaft rotating at another particular speed. So you can keep ramping up or ramping down the speed of a gas compressor. So, and the third one is, of course, electric motors. Electric motors are probably the most efficient. You can get as high as 95 to 98% efficiency, or let's say 90 to 97, 98% easily. Because if you use a 4-pole motor with a 50 hertz power supply, it's 3000 RPM. At 60 hertz, it's 3600 RPM. But as I said, if you have to rev up the speed of a gas compressor, you will have to use a gearbox. So that's one way of doing it. Or you can also use a variable frequency drive. So if you use a gearbox, there's a certain limit to how much so let's say you have a motor which is running at 3000 RPM, and you have a gas compressor rotating at 6000 RPM. So gear ratio is 2:1. That's it. You can't do anything about it. But then if you want to continue to alter the speed, then you have to go for a variable frequency drive, which is nothing but a piece of electronic circuitry that's fitted onto to an induction motor with some ventilation, because the way a VFD works is that you're altering the frequency of the current that is going into the motor. So that way you keep altering the speed at which the motor runs, which in turn drives the gas compressor. Now earlier, I think if I remember, somewhere in 2001, 2 or 3, somewhere around that time, about 20 years ago, I think the highest was about 20 megawatts with an electric motor. But then, no, not 20 megawatts. I think up to 45 megawatts for Qatar gas, something I worked on. So 45 megawatts, which can run up to 60 megawatts for 90 seconds. In I think QG2, Qatar gas 2. So the thing is that with time, what has happened is that electric motors are much more suitable than gas turbines, because you don't have emissions. You have the advantage of a variable frequency drive, but if your power rating goes up, it's going to generate a lot of heat. So it's not always very efficient in that sense. Then you reduce civil works. You don't have to worry about a steam system, water polishing, a boiler, or like a gas turbine where you have extremely high temperatures and also emission problems. So the key takeaway is that the way we choose a driver to run a gas turbine first depends on the compression capacity. If you can't get a gas turbine, if you can't get a gas turbine to provide that much energy to a compressor, maybe you can use a steam turbine. But anyway, we don't really run it to that extent unless they are these mega projects like in LNG liquefaction plants, where you can have up to about 150, 160 megawatts. So that time what we do is that we couple a gas turbine with an electric motor. That's one way. So depending on the capacity, we choose the driver. Second, the compressor configuration. Then the plant location. Like I said, if you're in the middle of nowhere, no water, no power, then you'll have to go for a gas turbine. You draw out a portion of the gas from the wells and route it to a gas turbine. Then what kind of fuel do you have? Because nowadays you have gas turbines where you can switch the fuel that you use. So when you start a gas turbine, you need a fuel which has very high calorific value. So maybe you can start it with hydrogen and then switch over to natural gas. And then flexibility of operation, which is whether you need to alter the speed. So do you need a variable speed drive or a fixed speed drive? So what I've put here is 5 basic criteria that you need to consider when you choose your driver for the gas turbine. For the gas compressor. Next. Yeah, so what I've put here is a very basic arrangement of a single stage gas compressor. Now, every gas compressor would have more or less the same elements. Oh, so the first thing is, yes, you need a suction and discharge block valve. Then you'll have a suction scrubber, a gas compressor with its motor, a cooler, a discharge cooler, and an anti-surge line. So the suction scrubber is, of course, to remove any liquids in the system. Sometimes you can even have particulate matter forming. If you have hydrates forming inside the piping somewhere, the suction scrubber will collect it. You can have the suction scrubber. After the suction scrubber, sometimes we put a cone filter, or we call them cone strainers. So it looks like a wizard's hat that you place it horizontally. So during commissioning, what happens is that it collects all the debris, and they can be temporary or permanent. So I haven't shown that here, but you can put a strainer here in the suction line. Then the gas compressor, of course, and then you have to put a check valve at the discharge. The check valve is to prevent any reversal of flow. Now, when you compress a gas, its temperature will rise. So you have to cool it. So you put an air cooler here. And then you put one more discharge valve, and this is a must. The one that I've, the box, sorry. You'll have to help me, sir. I'm not. Yeah, okay. So you have to put this check valve here. It's a must. I'll explain why I said that. And then, of course, an anti-surge line. Now, like I said in the beginning, you cannot operate a gas compressor closer to the surge line. Now, surge means, let me put it this way. What we are taught is any fluid will flow from a region of higher pressure to a lower pressure. But in a gas compressor, it's the other way around. So let's say at the suction, you've got 2 bar pressure, and on the discharge, you have, let's say, 8 bar pressure. Now, the thing is, why is it that the gas is flowing from 2 bar, which is at lower, which represents a lower value, to 8 bar, which is higher value? That's because we are doing work on the gas. We are raising its pressure. Now, let's say we trip the compressor, we cut off the power supply, let's say. What happens is that the discharge pressure, which is higher at 8 bar, will flow backwards. It will flow back into the compressor. So you have 2 bar here, 8 bar here. The pressure is rising because we're doing work on the gas with a prime mover. The moment we cut off the power supply, the gas from the discharge will flow back into the compressor, and that can cause mechanical damage. Sometimes very severely, to the point where you'll have to just throw away the machine. So surge is a phenomenon where there is a flow reversal of gas from the discharge side back to the suction side, and we don't want that to happen. So if we do not want that to happen, what we do is we have to play, we provide a D2 called an anti-surge line. So the volume of gas that is sitting in the discharge line will simply flow back to the suction via an anti-surge line. So let's say when the gas compressor is running, if I open the anti-surge line, some of the gas which is flowing forward will start to get recycled back inside. So the main purpose of the anti-surge valve, it's a control valve, really speaking. It's no different from any other control valve, except that the purpose of an anti-surge valve is to prevent the compressor from surging. The second thing is that the anti-surge control, the AS, I'll use a few abbreviations because, so anti-surge valve is ASV, anti-surge control is ASC, let me put it that way. So to control the anti-surge valve, it has to take readings from the suction line. It has to know when it has to open and when it has to close. And for that purpose, what we do is we place a PT, a pressure transmitter, TT, temperature, FT, flow transmitter. So we put an orifice here from where, and then we hook a transmitter to it, and it sends a signal to the anti-surge controller. So depending on the suction and discharge conditions, pressure and temperature, what the anti-surge controller will do is apply, will apply this expression, the polytropic head versus the polytropic head. It reads the inlet temperature, the molecular weight, the pressure ratio, and it tries to see how far it is from the surge line. So that is the main purpose. That's the main purpose of the anti-surge controller. So the anti-surge control system consists of basically a PT, TT, and an FT. One on the discharge, one on the suction. It takes all the readings and compares it and computes how far the operating point is away from the surge line, and decides if the ASV has to open up or not. So if you observed, I put a check valve here, and this is a must. This check valve, after the anti-surge takeoff, this is a must, because what happens is when we open the anti-surge valve, it's not just the discharge side volume that will flow back into the suction. You can have the gas in the downstream also competing with the discharge volume to flow into the anti-surge line, and we don't want that to happen. So by putting a check valve here, we are isolating the compressor module from the downstream equipment. And by doing so, what is happening is only the discharge side of the volume is getting recycled back. So the key takeaway of the slide is you need a suction scrubber. You will need a discharge side check valve. For sure, one after the anti-surge takeoff. We also put a check valve at the discharge flange, you need an air cooler to cool the the compressed gas. And you also put a vent valve, because sometimes you have to, not sometimes, I mean, during operations, you will have to vent some gas to prevent the gas compressor from surging. And then you have an anti-surge valve to recycle the gas. I've put some notes here because I'll make the slides available for all of you the moment the session is over. So they've put some notes here to follow. But in the interest of, just to keep, to avoid, yeah. So the next thing is, you have to know how a gas compressor is started. First, the thing is that, I mean, let me put it this way. Shutdown, yeah. So let's say you walked into a facility, you saw your gas compressor running. Now, the way we shut down a gas compressor is you have to open the anti-surge valve first. When you do that, the operating point moves from its rated point towards the stone wall region. But the thing is that you don't size it in such a way that it moves all the way to the stone wall region. You have to open the anti-surge valve so that there is a recycle in the line, and then you trip the compressor. When you trip the compressor, the operating point goes to zero. That is, the flow rate through the gas compressor starts to decrease. Now, if you look at this graph, this line is not crossing the surge line. So this is a safe shutdown. But suppose, let's say it started to cross during a shutdown. What happens is that, I mean, there could be a number of reasons. One, the anti-surge valve is undersized. But for now, I'll just leave it at that. It could mean that the anti-surge valve is undersized. So in a normal shutdown, what happens is that we open the anti-surge valve and then trip the gas compressor, and then close the suction and discharge block valves. When we do that, there is gas which is, I mean, it'll continue to get recycled, but then it'll come to the flow of gas will come to a halt. When that happens, it reaches a certain pressure and temperature called the settle-out pressure and settle-out temperature. The thing is that when you shut down a gas compressor, if you try to restart it, it won't. Because at settle-out conditions, what happens is that the gas grips onto the rotor so tightly that the driver is unable to again restart the gas compressor. So what we do is we open the vent valve and we depressurize the system. In doing so, we are reducing the settle-out pressure inside. And then if you try to restart the compressor, you shouldn't have any problems at all. So what happens during a normal shutdown or a planned shutdown is you open the anti-surge valve and then you trip the compressor. When you do that, the gas in the piping reaches settle-out conditions. If you try to restart it, it is not always possible. So you open the vent valve. What happens is that the way the logic is programmed is that sometimes we just it's automatic. So the moment the compressor is stripped, it comes to a grinding halt. The vent valve will open after some time and depressurize the system, and then you can restart it again. That's a normal shutdown. But then if you want to restart it, if you want to restart, what you do is you continue to keep the anti-surge valve open. You open the suction block valve, but keep the discharge block valve closed, and then you ramp up the speed of a gas compressor. When you do that, the operating points goes from zero all the way to the rated curve, but not to the rated point. So at that time, once it reaches the rated curve, you start closing the anti-surge valve while opening the discharge block valve. When you do that, the operating point will go to the rated point. So in short, whether you're going to start a compressor or shut down a compressor, we open the anti-surge valve first, and then we trip the compressor. If you want to start up, keep the anti-surge valve opened, and then ramp up the speed in the case of a startup. Now, sometimes what happens is that, let's say you had a power failure with an electric motor, and there was a power outage, let's say. Okay, so let's say your anti-surge valve is undersized, and there was a sudden power outage in the facility. And you know what happens? the operating point can cross the surge line. So this is an example of an improper shutdown. This is a case of surging. Now, this is just a simulation output, but in reality, what happens is that you see these oscillations, there will be many more till it goes to zero. So we don't want to see a curve which looks like this. We don't want to see any point which is on the left-hand side of the surge line. So this is a case of an improper shutdown where the anti-surge valve was undersized. So one solution to this is that you increase the ASV size, one of the solutions. So if you do that, so you see in this is a case of an emergency shutdown. The power, the power to the driver was cut off. So the compressor starts to coast down, and then you open the anti-surge valve. Because the anti-surge valve is undersized, we provide one more route to recycle it. And we call it a hot gas bypass. The difference between an anti-surge valve or a cold recycle line is because this line is taken after the cooler. So you're cooling the gas to recycle it. That's why we say cold recycle or anti-surge line, valve, recycle, whatever. But here, a hot gas valve is like a short circuit. Directly, whatever is the discharge gas at whatever temperature it may be, we simply recycle it back to the suction. In doing so, what we are doing is maintaining a forward flow at all times. So in this case, with a hot gas bypass and an anti-surge valve, for the case of an emergency shutdown, the operating point was going closer to the surge line, but because we are able to recycle enough, we are staying away from the surge line. So what dynamic simulation engineers do is this. Their job, the first job is to ensure that whatever elements they are putting into their gas compressor system must ensure that the operating point never crosses the surge line. That's all they do day in, day out. I mean, at least one of the aspects of their job. This is not the only one, but is one of the important jobs. We do not want any gas compressor from surging, or we lose the guarantees and warranties from the vendor. So to summarize, whether it's a startup, a normal shutdown, or an emergency shutdown, do whatever it takes to prevent the operating point from crossing the surge line. In the case of a shutdown, normal shutdown, it's a planned shutdown. We open the anti-surge valve and then trip the compressor. In the case of an emergency shutdown, after the compressor trips, the anti-surge valve opens up. During a startup, we keep the anti-surge valve open and then we ramp up the speed. So this is a summary of, I mean, because when you're doing the simulation, a dynamic simulation, you need to know a little bit of basic of how a gas compressor is operated. Then it becomes moving. Okay. So this, okay, so the next thing is that, now in the previous slide, I talked about hot gas bypass. Now the hot gas bypass is a last resort, because when you try to recycle too much hot gas back into the compressor casing, you're actually overheating the gas compressor. You can have lube oil getting too hot, any additives in them precipitating out, or you can have some charring, forms a carbon soot over there. The damage can happen in so many ways. So we do not want to have excessive temperatures inside a gas compressor when it is running. Now, the hot gas bypass is a last resort, but what is it that I can do before using hot gas bypass as a last resort? I'm not sure if people are able to see this, the diagrams in this page clearly, but in case you cannot, let me know. I'll try to zoom in here. Oh, all right, let me zoom now. Yeah. Going there? Yeah. Okay, so the first thing is that if you think you're, let's say you're doing your dynamic simulation and you think the gas compressor is surging, one way is to increase the anti-surge valve size. But please understand there is an upper limit to how much you can increase the anti-surge valve size. In case because the size of the anti-surge valve determines how much you can recycle, but how quickly you can open the anti-surge valve decides the response time of the anti-surge controller. So in case the anti-surge valve is taking a long time to open up, so let's say you have a large 16-inch valve, really big, large machines where you have a 16-inch valve, let's say, and it takes at least a good 2 seconds to open up, and that's that's not providing you with enough a quick response time to attend to surge. Then what you can do is you can add a parallel quick opening valve, which is smaller in size. So if there's a 16-inch valve, maybe you can put maybe an 8-inch valve or a 4-inch valve. So, but then you have to. It's because a quick opening valve is really an on-off valve. So as quickly as possible, it opens up. So in case the anti-surge valve is lagging and you're not able to recycle enough, you put a quick opening valve. This is one way of doing it. But let's say despite putting in a quick opening valve, it is not solving your problem. And what you do is, slow. Then what you can do is, you can move the anti-surge tap-off point closer to the compressor discharge. That is, you reduce the distance between the discharge flange, the cooler, and the remaining part of the piping. You can, so in doing that, you're reducing the discharge side volume. So when you reduce the discharge side volume, the inventory is lower, and you can quickly transfer that back to the suction side when the anti-surge valve is opened. But there's a limit to how much you can push it closer to the discharge side, because you can have vibrations. If you push it too close, sometimes the anti-surge valve can also start rattling. So there's an upper limit to how much, there's a lower limit to how much you can reduce the distance between the anti-surge tap-off point and the compressor discharge flange. So by reducing the discharge side volume, you're reducing the inventory. With a lower amount of inventory, you can quickly transfer it back to the suction side. So this is one method. So let's say because of your layout, there's a limit to how much you can tinker around with this method. What you can do is, you can slow down the speed at which a compressor is coasting down. So let's say the plant is running and there was a power trip. The compressor is starting to coast down. The anti-surge valve opens, but you're not able to recycle enough flow back to the suction. Then what you do is you slow down the speed at which the compressor is coasting down. But there is a problem. This, but you see, in the case of an emergency shutdown, it's a waste of time. Because the moment there's a power cut, there's nothing to really, it's a free fall, the speed is just falling freely like that. There's very little that you can do. So it's only during a normal shutdown and with a variable frequency drive, this method works. So if you have a normal shutdown, because it's a planned shutdown, you open the anti-surge valve and you control the speed at which the speed is coasting down. That's the only advantage with this method. But in case of an emergency shutdown, it doesn't matter. It's just a free fall. The speed is a free fall. So this method has its limitations. But now let's say you didn't have it's not a case of normal shutdown. Then what you can do is, the next step is you simply reroute the entire piping. If it is a greenfield project, yes, it's possible, because if the plant has not been constructed, then what you can do is you can start thinking of revisiting the piping layout. Of course, the piping guys will be upset. And in case it's a brownfield job, it's an expansion where you're adding a parallel compressor. And if you have to reroute the entire plant piping, nobody's going to like it. But then this is still an option. I've just put it here. As long as your plant layout allows you to reroute the piping, you can touch it. But let's say this is also not possible. Then what you can do is you can use a vent valve. So that is, when your gas compressor, during a shutdown in your gas compressor, when the anti-surge valve is not able to recycle enough flow, you evacuate some of the gas through the vent valve. If it is an air compressor, not a problem at all because it's non-toxic. But if it is natural gas, I mean, you can route it to the flare. So the moment the anti-surge valve, let's say the compressor tripped, the anti-surge valve opened, but the compressor can still surge. You evacuate some of the gas through a vent valve. And if it is natural gas, you hook it to a flare. The problem is that you can have emissions. So it's not really a preferred choice in a way, but it's still doable. So in case you're not, because you have some, let's say you have natural gas, you have stringent emission standards, and you got some safety inspector watching you all the time, and you can't use this method, resort is to use a hot gas bypass. That is, it's moving so slowly. I mean, yeah. You use a hot gas bypass, because if all the other methods fail, by trying to reduce the discharge side inventory, by putting a quick opening valve, by trying to slow down the speed at which the compressor coasts down, and it is not allowing, I mean, but your system is not, in case of an ESD, it doesn't help anyway. And if you cannot, because if it's a brownfield job and because of the plant layout, there's very little you can do to alter the piping and the equipment locations, then just put a hot gas recycle. Like I said, the line which comes after the cooler is a cold recycle line, aka anti-surge line. But in a hot gas HGB, a hot gas line, is directly from the compressor discharge back to the suction. It's an on-off valve. It's a fail-open valve, which means if the instrument air fails to it, it goes full open. We wouldn't want to. Before dynamic simulation came into existence, what people used to say, I mean, at least on the drawings on the side, you would say, size the hot gas valve for 50% of the surge flow rate. But you don't have to always do that. With dynamic simulation, that's an advantage. Sometimes you need to recycle only maybe 10% or 20%. Too much hot gas, you overheat your gas compressor, your bearing temperatures will shoot up, your lube oil can lose its viscosity, you can have precipitation, precipitation of the additives, you can have I mean, apart from the bearings and the lube oil, if it is too hot, the trouble is that your settle out temperature also will be very high. So if the settle out temperature is very high, then there's only one way. You'll have to start venting the gas to a flare. So we don't want to overheat the compressor. That's the key takeaway to be mindful when you place a hot gas recycle. Then I think we got 15 more minutes. Let me, okay, I'll just come to the last part. Okay, settle out conditions, like I've said, the temperature and pressure at which a gas is locked inside the compressor piping after a shutdown is called settle out pressure and settle out temperature. If the SOP, settle out pressure, and SOT, settle out temperature, is high, there is too much inertia, and and it takes a lot of power to restart it. If the driver is not powerful enough, you'll have to vent some of the gas. The advantage with of conducting a dynamic simulation is to can't do it precisely, but at least you can predict a ballpark figure of how much should be the startup power. You can also estimate how much of the inventory has to be depressurized. So basically, how many dollars you're burning when you're depressurizing. And SOP and SOT are affected by the ambient conditions, because when you shut down a plant, there's heat exchange happening with the environment. But then for that to happen, you will have to keep the system idle for a very long time. But the ambient conditions still have an effect on the SOP and SOT. So higher the SOP and SOT, the more power you need to restart a compressor. So that's the key takeaway from this slide. The next one, this is, so for an, sorry. So what are the, I mean, this is a very old slide, but I'll tell you where the corrections are. So for an anti-surge valve, some of the key typical requirements are it has to respond quickly to surge. That means the valve must be able to open up in less than 2 seconds. Now, anywhere between, let's say you have up to a 4-inch valve, you can use a solenoid valve. Anywhere between 4-inch to 16-inch. I mean, these numbers are not absolute. These are just typical values that you can keep in mind. So anywhere between 4-inch to 16-inch, you can use pneumatic type of valves. 16-inch and above, you have to use motor operated valves. So physically you put a big motor on top of the valve, and when the signal is given, it quickly opens it up, and it has to happen in less than 2 seconds. I think there are, because for smaller valves, you can do it in, say, let's say 1.1 seconds. The smaller ones, like, I don't know, 6-inch, 8-inch, 10-inch, like that. And it has to be fail open. Fail open means the moment the instrument air fails to the anti-surge valve, it has to fail open. That is, the valve has to go open. If it doesn't open, the compressor will go into surge. Then you have to keep your fluid velocities less than 0.3 Mach to avoid any erosion in the piping, any valve damage. Sometimes extremely high velocities can cause, because you have very high pressures on the upstream of the anti-surge valve and very low pressure on the downstream, you can have JT cooling, Joule-Thomson cooling. And then if it is a hydrocarbon where you have sufficient water and methane, you can have hydrates forming. So, and those hydrates, what they can do is they can wear out the pipe, they can wear out the valve. Sometimes you can have cavitation, and because of cavitation, you can again have metal loss inside the valve. So try to keep the fluid velocities less than 0.3 Mach to avoid piping damage. And then the valve should be able to provide you stable throttling characteristics, which means that you don't want the valve to keep jumping up and down pretty fast. You don't want to see the valve shattering. It has to open up smoothly, and it has to close. You have to. It's like the valve can't keep opening and closing erratically. You want a very stable way of opening and closing. So we simply say stable throttling. Now here I've said the actuator's opening time. So the thing is that, let's say the compressor tripped. It takes a certain amount of time for the signal to reach the DCS or the local control panel. And from there, the signal again goes to the anti-surge valve to open up. So that is the time taken for the signal to go from the gas compressor to the DCS should be less than 100 milliseconds. Although I've put 300 milliseconds here, because of most of these slides, I made it, I think, more than 10 years ago. And I don't have the PowerPoint slide, so I'm not able to change it here. So I'm telling you where the corrections are. So we want the time taken for the signal from the gas compressor to reach the ASC or the DCS should be less than 100 milliseconds. And again, from the DCS to the anti-surge valve, let's say less than 100 milliseconds. So we want the lower the scan time, the quicker is the response time. And then naturally, when you operate the anti-surge valve, there will be noise. We don't want the noise to exceed 110 decibels. 85 decibels is acceptable. Then you can have. Then we come to the type of opening characteristics of the valve. Now, most manufacturers give you a linear opening valve. So CV versus Q. If you look at the graph of the graph, then it's a straight line. Most of them provide a linear opening characteristics. Some, what they do is they mix a linear with an equal percentage. So you can have the first part, which is linear, let's say up to 30 or 40%, and then the rest of the curve is equal percentage. The trouble with equal percentage is that up to 50% opening, it doesn't recycle enough. But we also but that's the time. But up to that 50% opening is the crucial time. So we try to avoid that first part of the curve by linearizing it, and then we put it's like a hybrid characteristic. So we mix a linear with an equal percentage. Equal percentage takes its own sweet time up to the first 50%. We don't want that to happen. We want a quicker response time. So we force the valve to open up faster by putting linear characteristics. Quick opening, it suffers from poor throttling characteristics. So we don't use quick opening valves for anti-surge valves. Then, so the key takeaway, you got to put a valve and a control system which has the smallest response time. The more quickly the anti-surge controller responds, that well you can protect the gas compressor from surging. And then, okay, just 5 more minutes, I'm done. And the next thing is, what are the various kinds of recycle arrangements? The first, the one that you're seeing here is basically a hot gas bypass. You don't have a cooler here, so the discharge volume is less, but there's a problem. Gas too high, you have a temperature here where if the compressor can trip. So this is only for very small pressure ratios. Let's say a pressure ratio of, as long as you can keep the temperature less than, I think, let's say 75, 60, 70 or 80 degrees Celsius, something. So you can't use this for high pressure ratios, small pressure ratios, let's say 1.1 or 1.2 pressure ratio like that. The second one is the standard where is what I've shown in the previous slides, and you will see it very often. You have a suction scrubber, you have a gas compressor, and you have a discharge cooler and the check valve to prevent any gas from the downstream also getting recycled through the cold recycle line. The advantage is, although I've written full recycle, it is not always possible, provided the temperature is low. You need very high cooling duties here at the discharge air cooler for full recycle to be able to operate in full recycle. So there are certain limitations with this, but this is a standard a configuration that you'll often find. But by adding an air cooler here, what happens is that you are increasing the discharge side volume, so more inventory. It takes a little more while to recycle all that back to the suction. So to avoid that, what we can do is to add a discharge side cooler. Now this configuration, the third one, number 3, allows you to go for full recycle, because every time, there's a for full recycle, provided this line, this takeoff point is actually happening after the air cooler. So again, you can't really do full recycle here. If the discharge tap-off point was kept after the discharge side air cooler, it is possible. But there's a problem. Because of the air cooler and the additional piping, again, you're increasing the inventory, the response time goes down. So the ideal way is to run a dynamic simulation and see, can I recycle enough gas to prevent the compressor from surging? So but by placing it just after the compressor discharge, you have a smaller discharge volume. The response time is quite high. The only thing is that because of this additional cooler, it's going to cost you more money. That's all. And then you have a cooler in the recycle line. The advantage is, because you don't have a cooler here, you're reducing the pressure loss. Now, when we design a system like this, we try to keep the total pressure loss across the suction and discharge side to less than 35 kilopascal, or 35 kilopascal is the max. We don't want it to exceed that. But by removing the cooler, you're reducing the inline pressure losses. But then, although I've said additional cooler here, well, it still represents a cost. You'll have to still put a cooler there. But again, this is not for high pressure ratios. This is for smaller pressure ratios. The advantage is that you can recycle, you can keep it recycling for longer in case you want to turn down production. But then there are limitations to even you putting a cooler in the recycle loop. So this is another configuration. Then the standard one which I showed there, you have a cold recycle and you have a hot recycle. So this is a case of hot gas bypass. And then number 6, you can have parallel recycle valves. The anti-surge valve, if it is taking too long to open, you can put a quick opening valve in parallel. So that way you can try to reduce you can improve the response time to attend to any search that is possible. And then, of course, you have series compressors where you can have a recycle valve, a cold recycle for the compressor, which is larger in size, and you can put an overall recycle line for the smaller compressor. So this is a case of a smaller compressor followed by a larger compressor. Although I've never seen a configuration like this before, but at least from the research paper I took, I saw this, so I put that. But number 8 is a more sensible thing to do. If you have series compressors, put a recycle line for each compressor, and you can put an overall recycle line to improve. Because what happens is, if the recycle valve in one of the compressor opens up, it starts to show its effect on the compressor before that. So to avoid that, you put an overall recycle line. So this is another way of doing it. So thing is that there is no hard and fast solution as to how you should be placing it. You got to choose the way you route your piping and equipment to ensure that the operating point never crosses the search line. So there's no point in saying that this is how we always do. Every system is different because the performance curves are different, the operating conditions are different, the position of the operating point on the performance curves are different, the kind of driver that you use is different. Sometimes you have fixed speed drives, sometimes you have variable speed drives. Then you can have series arrangement or parallel arrangement. If it is a brownfield job, you have an existing compressor, and if it is and if you have to add another parallel compressor, there is a limitation to how much you can play around with the pipe. So depending on the situation, you choose the configuration that is suitable for your application. That's the way to go about it. It's not like there are hard and fast rules of choosing how you want to place your the recycle arrangements. And then I think that's about it. Yeah. So at the end of this, I put 3 tutorials in case if anyone is interested in to self-learn. They're quite welcome to use this material. I've put one on some basic calculations. The second thing is on how to calculate your set load conditions. I mean, because your simulation will give you results, but how do you check it by hand? You can use this. But please note that the results here can be very conservative. In reality, it need not necessarily be that much conservative. And then I put one more on how do you size an anti-surge valve. I put this on LinkedIn in case you'd like to work out an example. I put some data. I put the results also with all the formulas and hand calculations as well, and you can work it out if you wish to. So this is homework in case you want to, do it all by yourselves. So that's about it. I mean,
All right.
I could have done this better if it was a classroom training, but I'm not really used to Zoom. But I hope I've not disappointed anybody, at least.
Thank you, sir. Thank you, sir. And so let's see what questions and answers we have.
Yeah.
Okay. All right. So let's go through.
I'll just relinquish yeah.
Okay. All right. Very good, sir. Talk a little more about hydrate formation. Tell us a little more about hydrate formation and what can happen there.
So let me just, Asar, you'll have to go to slide number 4. So the thing is that when you have methane and water, it's a sure shot recipe for hydrates to form, under the condition that you also have the requisite pressure and temperature. Now, the anti-surge valve is one place where it's because you see, let's say you have 20 bar pressure here at the suction, and you have 60 bar at the discharge. So 60 by 23 is to 1. That 60 bar pressure gas is going to get squeezed through the anti-surge valve to close to 20 bar pressure again. So when you have a when the pressure drops pretty drastically, what happens is you can have Joule-Thomson effect. Now that pressure, the JT effect, when there's a JT effect and the pressure and temperature drops drastically, and you have methane and some water in the fluid composition, you can have hydrates forming. So what that can do is it can clog the valve and prevent it from it can damage the valve seat also. So so when that happens, the anti-surge valve may not even open up at all. So what we can do, one way is to take a small 2-inch line from the discharge to a control valve, a temperature control valve, and route it to the ASV discharge. So every time the temperature is dropping below the hydrate temperature, you take a little bit of hot gas and heat up the cool gas at the downstream of the anti-surge valve. Hydrates can form anywhere in the hydrates can also form after a shutdown. So let's say somewhere in Canada and it's really cold over there, and you shut down your gas compressor. And so what happens is we heat trace the lines to keep the piping and the equipment warm. We use heat tracing, but let's say the heat tracing failed and there is gas inside the piping with some water in it. Then what can happen is you can still have hydrate formation in the piping simply because it is too cold. And because of those cold temperatures, the P and T inside the piping can move inside the hydrate curve and still form hydrates. So in extremely cold conditions where there isn't sufficient heat tracing, you can still have hydrates forming. You can have hydrates forming across the anti-surge line, for which one solution, at least, which I've tried, is to take some of the discharge gas, which is really hot, hook it to a TCV, a temperature control valve, and the temperature control valve reaches the downstream of the ASV valve. So every time the temperature downstream is going into the hydrate region, the TCV will open and heat it up to prevent any hydrates from forming. We do not want hydrates in any gas compressor piping or equipment, simply because it can erode the pipe, it can clog the valves and prevent your valve will simply not open. That's one of the risks with hydrate formation. The other problem is that if you have a PT or a TT, your instrumentation will not register any signals because the hydrates can prevent the sensors from detecting the actual conditions inside the line. So that's another reason why we have to avoid hydrates from forming.
Very good, sir. Very good, sir. Thank you very much for your knowledge sharing. I know I picked up quite a bit, and hopefully our participants did.
Yeah.
And we thank you. We thank you for your time, and
Yeah, sure, sir.
We'll definitely plan in the next few months. We'll have another webinar with our
Sure, sir.
speaker.
Yeah.
All right. Thank
Yeah.
you, sir. All right. Thanks.
You're welcome,
Thanks,
sir.
guys.
Thank you
Thanks,
very
guys, for
much.
joining. Thanks, guys, for
Bye-bye.
joining. Okay.
Yeah. Bye-bye.
Okay. All right. Bye-bye.